The next in our series of medalist speakers is Rafael Navarro-Gonzalez, talking about Mars-like soils in the Atacama Desert, Chile.
Yes. Okay, the title of my talk is Mars-like soils in the Atacama Desert, Chile. If we want to look for life elsewhere, we need to understand what are the requirements of life on Earth. And basically what life requires is a source of energy. For autotrophs, this is sunlight. For heterotrophs, this is for chemotrophs, is inorganic compounds. And for heterotrophs, they need organic compounds. It's also necessary a carbon source. This can be organic or inorganic. There is the requirement of liquid water, and there are other elements. In the search for life elsewhere, beyond the Earth, basically what we require is the strategy to follow first the water. If we find liquid water, there's a good chance that we can have life. Once we have identified the place where water is available, then we need to search for organic compounds. Now, organics can be produced abiotically, or they can produce biologically. So if we are able to detect organics somewhere beyond the Earth, the next logical step will be to detect life by itself. And this is the Mars exploration program that is trying to understand whether Mars was, is, or can be a habitable world. Mars has been a very interesting planet. It has the more number of space missions so far. Up to now, we have about 41 missions. You can see they began from the early 60s. There's a gap of interest. This is basically due to the Viking results that we'll review in a moment. And then there is a great interest, especially after we have discovered that we have rocks from Mars that landed in several regions of the planet. And we are right now in about the next mission that is trying to explore if there is life on the surface of Mars. This is a projection of the surface of Mars. There are several missions that have already been landed. Some have luck, some fail, like Mars 3 and Beagle 2. But of all these missions, probably the one that has all the approaches in searching for liquid water, looking for organics, and searching for evidence of life were the Viking missions. These missions were twin missions. They were sent in the middle of the 70s, and they began retrieving data 1 year later. The mission analyzed surface soil. So it has a scoop that can get soil from the surface down to about 10 centimeters in depth. In some cases, it was interesting to look at soil that was covered by sunlight. So the scoop could move one of the rocks and get soil under the rock. There were 3 experiments that they were conducted. The first one was to see whether there was photosynthetic life. In photosynthesis, bacteria or plants take carbon dioxide, they use sunlight, and they produce hydrocarbons. Since it wasn't clear what kind of source of carbons Martian bacteria could use, they use isotopically labeled carbon dioxide and carbon monoxide. After several days of incubation, if there were bacteria in the soil, these bacteria were to convert these carbon salts into organic compounds. Then the gases that were unreacted were pumped down, and the salt was heated to about 750 degrees in the presence of oxidizing. So if there were organic compounds, these organic compounds were going to be oxidized to CO2, and they could be detected. What it was surprising is that the results were positive. However, there was a big difference with what it was expected. The amount of fixation was about 100 picomoles per centimeter cubic. But what it was interesting is that this fixation was decreased in the dark. In photosynthesis, this takes place only during the day. And also what it was puzzling is that it was inhibited by moisture. In the case of bacterial photosynthesis, this is not the case. Actually, it's promoted by moisture. There was a second experiment. This was the gas exchange experiment. All organisms are continuously exchanging gases with the environment. And the idea was to try to get soil from the surface of Mars. It was injected in a chamber. Then water and nutrients were added. If there were bacteria, we would expect some release of gases. And surprisingly, there was release of oxygen. The amount of oxygen released was about 70 to 800 nanomoles per cubic centimeter. But what it was surprising about this experiment is that if you were to have bacteria and you add more water, more nutrients, one would expect to have more oxygen release. And in this case, there was only release of oxygen with the first contact of water with the Martian soil. So this result, even though it was positive, indicated probably the reactivity of the Martian soil by chemical processes. There was a third experiment, and this was the more controversial one. The idea was to take Martian soil, put it in a chamber, then a broth of nutrients were added to it. This broth contained formate, amino acids, and some acids. And the idea was if there were bacteria, the bacteria were going to destroy these organics into small building blocks, basically carbon dioxide. And what it was interesting about this result is that it was positive and the response was exactly as it was expected from bacteria. Here you can see, for instance, the time in hours of incubation. Once the soil was added to this broth of nutrients, you can see the radioactivity that is released by the gases. If you heat the soil to maybe 150 degrees for 2-3 hours, bacteria are sterilized, and you can see that there is no more production of this isotopically labeled carbon dioxide. These are the results of the Viking mission. After a few days of incubation, you can see that there is a rapid release of carbon dioxide, and when this soil was heated to 160 degrees for 3 hours, there was no more release. When the scientists discovered this, they were very excited because they thought they have the first evidence of extraterrestrial life. There was another experiment on the Viking mission that was not intended to search for life, but it was crucial to the arriving to the conclusions of whether there was or not life on Mars. Yeah, and this is to take soil from the Martian surface, then the soil is heated in a chamber. If there were bacteria or molecules, organic molecules, these are going to be cleaved into small molecules, and you can separate the molecules into, well, the mixture into individual compounds, and then they are identified by mass spectrometry. This is the typical spectrum that you can get from the dry valleys. This is a very dry desert in Antarctica. The number of bacteria here is extremely large compared to other places in the world, like the Atacama, but nonetheless is very small compared to the soils that we have, for instance, here in the garden or on these spots. But when they repeated this experiment on Mars, what it was discovered is that there was no compounds. There was some peaks, but this is in the level of noise. There were some concern whether there was some failure of this instrument, because it was surprising that there were no organic compounds. There was a debate among the scientists of these experiments, but since the experiment was running for more than a year, it was possible to detect in some cases some compounds like methyl chloride that actually was a contaminant, a terrestrial contaminant that was used during the pre-building of the Viking mission to clean the instruments on the spacecraft from organic compounds. So the presence of this terrestrial contaminant was used as an evidence, strong evidence, that the mass spectrometer was operating correctly. And then what it was concluded is that there were no organic compounds on the surface of Mars. If they were present, they should be in the range of 1 to 10 parts per billion. And there were detection of these terrestrial contaminants like methyl chloride or fluoroethers. There was only detection of small inorganic molecules like carbon dioxide and water. This was a big surprise because even if there were no life on Mars, one would expect the delivery of organic compounds. For instance, meteorites delivered every year about 2.4 times to the 8 grams of organic carbons. If we consider destruction mechanisms by UV, we end up with about 10% survival of these organic compounds. Over a period of 3.5 billion years, we can have about 365 parts per million of organic carbons. But why they were not detected? And so it was speculated that there was some oxidant probably produced by UV light on the surface of Mars, maybe some peroxides or superoxides, that they oxidize the organic matter to CO2. There has been some controversy over the years about the label release experiment that gave positive results versus the organic detection. And so some of the suggestions have been that there is a strong oxidant like these superoxides that can contribute to the destruction of organics. There is a thermally stable peroxide like hydrogen peroxide, and there's a weak oxidant like iron oxides. There have been some experiments on the laboratory at that time to try to understand the response of these biological experiments. For instance, if you take silicates and you introduce water vapor to them and you irradiate with UV light, you produce hydrogen peroxide, and then when you add water, you release oxygen. And this is equivalent to the experiment that was used for exchanging gases. Then the other experiment that was controversial, the one that destroyed the organics in the same kinetic that it was expected for life, they repeated the experiment, but this time they added hydrogen peroxide, the oxidizing species that was thought to be present on the Martian surface. And what you can see is that the same kinetic pattern that you observe on Mars is the one that you produce with hydrogen peroxide. So based on these results, the conclusions of the Viking results indicated that there were no organics on the surface of Mars, at least at the parts per billion levels. Even though these levels are very small, you can calculate how many bacteria could be present in the soil of Mars, and there should be about 1 million bacteria per gram of soil. This appears to be like a large number, but if you look at the number of bacteria on the soil on any garden, the number is 1 billion, 1 million of 1 billion cells per gram of soil. And there's something on the soil that is so reactive that is destroying the organic compounds, and the more likely oxidants are hydrogen peroxide and superoxides. Now, these results were very puzzling. There was no more interesting to go to Mars until we discovered that we have rocks on Earth that came from Mars, and it begins the new interest to go back to Mars. But now we have more information about what are the conditions of the Martian surface. We know that Mars looks like a desert, And we have many deserts on the planet. Here you can see a picture of the deserts. Actually, in North America, close to NASA, where these experiments were done initially, we have several deserts. Of all these regions, the driest part is the Mojave in California, but this looks like a jungle compared to other places on Earth, especially the Atacama, where we have been working over the last 6 or 8 years. Well, the Atacama Desert is quite long. It extends about 1,000 kilometers between 20 degrees south to 30 degrees south. This is just considering Chile because it also continues into Peru. But this is one of the driest places on the planet. It is certainly the oldest desert on the planet. The age of it has been calculated at about 10 to 15 million years old. And what is surprising is that this is the only place on the planet that we have large ores of nitrates. Nitrates are very, very soluble. They are typically rained down as acid rain, but in places that it doesn't rain, it is deposited by aerosol deposition. And because it doesn't rain on this region of the Atacama, they can accumulate. And this is the only place where you can find large accumulation of nitrates. This is a topographical view of the Atacama Desert. On the east, you see the Andes. The Andes are quite big. Typically, they range between 5 to 6 kilometers. The moisture that is coming from the Atlantic through the Amazonia cannot penetrate into the Andes because of orographic precipitation. All the rain precipitates, well, all the water precipitates on the eastern part of the Andes. And by the time the air gets into the upper Andes or the Central Valley, it's completely dry. On the west part, we have the Atlantic Ocean. The ocean has cold waters. These are the Humboldt currents coming from the South Pole. And because of the cold temperature, the clouds are not highly convective. The deck of the clouds is about below 1,000 meters. And we have the coastal range that is about 1,000 to 2,000 meters. So there's a geographic barrier for these Pacific clouds to penetrate into the central depression that is the Atacama Desert. This is the typical weather that you see in the Pacific. There's usually an anticyclonic circulation, high pressure, that prevents the moisture from the Pacific to come into the coast. On this region in Bolivia, you have an anticyclone high pressure vortex. During the summertime, this high pressure system moves to the south, and this allows the possibility of injection of water from this Bolivian high into the Atacama Desert. Now, during the winter time, this high pressure system moves to the north, but it oscillates moving to the east and west, basically by the Niño effect. When this high pressure moves to the west, there is a moisture coming from this throw that penetrates into the Atacama Desert. So it doesn't rain in the Atacama, but from time to time it occurs. And this is the rain pattern of the Atacama. The line is the boundary. To the north and east, you have the summer rain, and to the south and the west, you have the winter rain. Basically, the rain occurs in the mountains and in the coastal region. This is the values of rain that you can get. For instance, in the Cordillera, just near the Andes, you can get precipitations of the order of 10 to about 200 millimeters per year. In the coastal region, you can get from 1 to 100, but in the Central Valley, you get values from 0.1 to about 10 millimeters per year. This is the only place on Earth that I've seen people talking about never seeing rain in their lifetime. I thought that rain was something that it was common to all of us, but no, not in this region. People of all ages sometimes never seen the rain. This is how the rain varies with latitude. For instance, the driest place on the Atacama is on the north, about 18 degrees south, and the wettest part is La Serena, about precipitation of the order of 30 millimeters per year. There's another source of moisture in the Atacama, especially to the north, and this is fog. The local people in Chile, they call it camanchacas. This is the clouds that penetrate into the mountains. And where this happens, you can see oases. This is like a jungle in the Atacama. I've never seen these oases except on the contact of the clouds with the region. It doesn't rain, it's just plants that can catch, get the water from the fog. There are studies about using fog traps, and you can calculate how much water you can get per year. And here I have plotted the amount of water that you can get per day. So the maximum amount of water that you can get is at about 500 to 800 meters in height. In red, you can see also gypsum. Gypsum is coming from sulfate that is coming from the ocean, from the Pacific Ocean, is being deposited on the landscape, and you can see the effect of this sulfate from the isotopes. The marine value is about 21, and you can see that near the coast, the value matches perfectly with marine sulfate, and then as you go inland, these values drop. These contributions from the Andes. But in altitudes between 400 to about 1,050 meters, you have strong contribution of humidity from fog. We have done extensive survey of the Atacama Desert in a precipitation gradient coming from the wet region. This is south of Copiapo. You can see a picture of that region here. This looks like the Mojave Desert, the driest part of North America. You see plants and animals. Then we move a little north, like 100 kilometers on the north of Copiapo. You can see, maybe not here, but if you look at close inspection, you can see some lichens, fungi, even ants we have found. But as you move north to this region, this is the only place I've walked on the earth that you don't see anything alive microscopically. You don't see birds, snakes, mice, nothing, insects. But what was surprising is this region. This is the core of the Atacama, the driest place on earth, and probably the only place that is sterile. We have sampled the place in the same mode that the Viking did. We analyzed just surface sample. This is my colleague from Louisiana State University. We collected 2 bags of soil. One bag went to the US for microbial analysis. The other bag came to my lab for organic analysis. And I tried to repeat the same protocol of the Viking mission for this analysis. This is just to show that they are about the same type of sampling. This is a pyrogram of bacteria from the Atacama that was cultured in the laboratory. You can see that there's a large number of compounds that are produced when the bacteria are heated to about 750 degrees. And this is the typical spectrum that you can get, a huge amount of organic compounds. Now, when we did the first analysis on the Atacama, on the core region, it was surprising to see that basically there were no organic compounds. By that time, we were studying Pico de Orizaba, the highest mountain in Mexico. There is also a transition of organic compounds going from low altitudes to high altitudes. The organic level drops, but the pattern of the organics is very similar. In this case, basically, there were only 2 compounds. One was highly oxidizing, formic acid. The other was a benzene. an aromatic compound, and these were the only compounds that were found in the Atacama. Now, I have to stress that for detecting these compounds, I have to use higher temperatures, 750 degrees. If I use the Viking protocol, that the highest temperature was 500 degrees, we don't see the organics. This is a pyrogram on the southern part of the Atacama region, where you can clearly see that there is a lot of plants. We didn't sample in the plants, we sampled where there were no plants, but you can see that there are a number of organic compounds in this region, indicating that there are live or organic compounds. If we plot the results from this transect, you can see in blue the concentration of formic acid. We have high levels of formic acid in the dry region. Then as we go to a more wet region, the values drop, and then they increase again. For the case of benzene, the organic compound, the concentrations are very low at the beginning, and they increase. What was surprising is if we plot the ratio of formic acid to benzene, and what we have is a proxy that can be used to detect hyperaridity. The highest values are telling us where basically it doesn't rain. The levels of organic compounds are very low. The nature of these organics are mostly oxidized. And here in the last plot, you have the bacterial counts. These are bacteria that were cultured in different media, and then you count how many bacteria they grow. And typically, they have values of about 10 million bacteria per gram. But then as you reach to this level, the amount of bacteria drastically drops, and basically we have bacteria detection at the limit of sensitivity. Also, the amount of diversity of bacteria changes with a precipitation gradient. This is the amount of bacteria that we have in the south, about maybe 12 different species. This is the number of bacteria that we have just at the place where they drop significantly. We only have 2 types of bacteria. So this is the first place that we have discovered on the planet that there is no bacteria life. There's no organisms living in the region. This is an excellent place to work all day, get dirty with your hands, and then you don't have to worry about eating your lunch. You can eat it and be sure not to get sick. We have also done studies because you not always culture the organisms that are present in the soil. So we have done culture-independent approach in which we extract the DNA from the soil, we amplify it by PCR, and then we try to identify to what type of organisms they belong. And this is for the wettest region. We have a number of bacteria that are present in just 1 degree to the north. We also see a lot of bacterial diversity, but what it was surprising is that in Yungay region, in the region that is sterile, we don't find even dead bacteria. We don't find DNA. So this is the first time we have discovered a place on the planet that the levels of organic are extremely low, there's no bacteria, and there's no DNA. This place just looks like Mars. You can walk here and you really feel that you are walking on another planet. What we have discussed or tried to analyze, maybe there's no bacteria on this region because there's something toxic in the soil. So to test about the toxicity of the soil, what we did is we took 2 soil samples. One is coming from the core of the Atacama, where there are no bacteria. The other is coming from the south of the Copiapo River, when we have about 10 million bacteria growing per gram. And we have mixed these 2 soils in different proportions, like for instance, 3 grams of one and 2 of the other, or vice versa, or the same amount. And what we see when we culture this is that we get, in all cases, bacteria growing, and the number of bacteria that we observe depends only on the dilution that you have done. So with these experiments, we've demonstrated that there is nothing toxic in the soil for the bacteria to grow. So there's no toxicity. And finally, we have repeated this famous controversial experiment that was done on Mars, the label release experiment, in which you took the soil from Mars, you add a broth with organic compounds. But in this case, we did the experiment with 3 sets of organic compounds. The first one was with formic acid. Formic acid is a very simple compound that can be easily destroyed by bacteria, but also can be destroyed by chemical processes. And we won't be able to distinguish if it was done by abiotic process or biological process. But then we devised a set of experiments in which we have alanine and glucose. Now, these 2 compounds have isomeric forms. For instance, life on Earth can only use L-alanine and D-glucose, but in another set of experiments, we have the opposite chirality, D-alanine and L-glucose. This is like, for instance, trying to use your right hand and try to use the left glove. It doesn't fit. Well, the bacteria has just the right enzyme to use this set of amino acid compounds, L-alanine and D-glucose. So if we get the composition by this set of experiments, it's telling us that the reaction is due by biology. But if we get this set of reactions taking place, it's indicating that there is an abiotic process going on in the soil. And these are the results. On the top, you have the decomposition of formic acid. You can clearly see that you have higher decomposition in the south, where you have more humidity, there is more life, but we cannot distinguish in this whether this is done by biology itself or there is a abiotic contribution. Here you have in blue the abiotic response. These are the organic compounds that biology cannot use, and in red you have the chirality that is used by bacteria. And you see that basically they decompose at the same level in the core region of the Atacama, and it's only when you move to the south that the abiotic response goes up. So we have demonstrated by these experiments that there's something in the soil of the Atacama Desert that is highly reactive, that is decomposing the organic compounds in the same mode that the Viking experiments were conducted. We have done further analysis. This has not been published yet, but we have studied, our initial study came from the south to the core region of the Atacama, and now we have moved from the central region of the Atacama into the north of Chile and into Peru. These are the results. In blue, you have formic acid. In red, you have benzene, and the ratio of this is telling you the hyperaridity of the region. We have the highest level here at Yungay region, about this area here. And then as you go to the north, these values drop and then they increase. The reason for that is that you have here the coastal range. The coastal range is higher precisely at this latitude that we have been working in the core region. And then as you move to the north, the coastal range drops, so you have possibilities of fog coming into the region. So even though it doesn't rain in the north of the Atacama, you have fog incursions that is preventing the development of Mars-like soils. We have done studies east and west. In the west, you have a moisture incursion from the fog. To the west, you have rain from the pre-Andes. And here you have the ratio of formic acid to benzene, and we have the maximum value at about the core region in the Central Valley. In black, you can see the nitrate deposits. Basically, it coincides with the higher hyperaridity. We have also discovered, and other people working in the Atacama Desert has found a strong variability of data. There are some places that you have low values of organics and low levels of bacteria counts, but then you move 10 meters or more, and you have high values of organics and no bacterial counts, or no organics and high bacterial counts. And what we have done is an extensive study just in the core region of the Atacama. And what we have done is plotted here altitude versus total organic matter in the soil. And you can see that the highest values of organic compounds are precisely at the lower altitude. The same is true with colony forming units. We have higher values at low altitude, and then as you go to the higher levels, then you have very low levels of organic and low levels of bacterial counts. We are suggesting that this patchiness that we observe in the Atacama is due by coastal fog that can income from the coast into the region, and only the highest place are prevented by this incursion of fog. So this is where you have the driest place on the Atacama. We've done also subsurface analysis. All these experiments I've discussed were only done within 0 to 10 centimeters in depth. But if you do experiments up to 1 meter in depth, we see life in the Atacama, even in the driest region. But this life can change from about maybe 40 centimeters to some places like 10, 20 centimeters. So there is life underneath, but there's no life on the surface. This is stressing how important is the sampling protocol when one goes to Mars. This is what I claim to be the extent of the Mars-like soils in the Atacama. This is the Jungle region, so it extends a few tens of kilometers west and east, and 100 kilometers to the south. This is an excellent place to do studies for exploration on Mars. This is a comparison about the Atacama Desert and Mars. In both places, we find very low levels of organics, no microorganisms, there's no DNA on Atacama, and there's a presence of unidentified oxidant on Mars. This we published in Science in 2003. If there would be an alien civilization coming to the solar system and coming to Mars, and they were to use the same technology that the NASA used for Viking, and this spacecraft decided to land in South America, specifically in the Jungle region, their conclusions would be there's no life on Earth. But of course, this would be the only place that could happen. This place, at the beginning, we were claiming it looks like Mars. Last year, Phoenix landed on the Arctic Circle of Mars, and now Phoenix claims that they have landed in a place that is similar to the Atacama Desert. The reason is that they have discovered the presence of perchlorates, and these perchlorates are deposited and accumulated in about the same areas where we find nitrates. Now, Phoenix has unable to detect nitrates on Mars, but there is evidence of perchlorates, so there's a good correlation about what we have discovered in the Atacama that looks like Mars, but also there's new data coming from Phoenix that indicates that Mars looks like the Atacama. Now, after we have discovered this place, this area has become very interesting, not only by NASA, but also by ESA, to try to develop and test new methodologies and new instrumentation. It's easy to detect that there was life on the Atacama, and it's cheaper to do that than to send the mission to Mars. Life in the Atacama disappeared about 10 to 15 million years ago in the surface. On Mars, life probably disappeared in the surface 3.5 billion years ago. So it will be simpler to try to test all the instruments and the methods in the Atacama before sending them to Mars. Well, the next missions that are being planned is the Mars Science Laboratory that was scheduled for launching the fall of this year, but this has been delayed 2 more years. And then by 2016, maybe 2018, ExoMars is also planning to go to Mars. So this will be an excellent place in the Atacama for testing these 2 instruments. And this work was done by a large team members. I would like to acknowledge Fred Rainey from Louisiana State University, Christopher McKay from NASA Ames, Richard Quinn and Frank Rutherner from SETI and JPL, and our colleagues in Chile, Luis Cáceres and Benito Gomez. I received funding for this work basically from my institute, the Institute of Nuclear Sciences, the National Autonomous University of Mexico, also another branch of the university that gives funding to researchers, the National Council of Science and Technology of Mexico, NASA Ames, and University of Antofagasta. And this is a picture of my team in the Atacama. And finally, I would also like to thank my family that came with me, my wife. My kids were unable to come, but my brother and his family are here, and I'm thankful also to them for receiving this distinction that I got today. Thank you very much. Yes, okay.
Are there any questions on this presentation? Yep.
So where would you look for life on Mars then?
I cannot hear.
Where would you look for life on Mars?
Well, NASA is trying to look where is evidence of water in the past. Opportunity and Phoenix has discovered jarosite and silica that is produced by liquid water. Also, Phoenix has discovered the presence of frozen water in the Arctic. So places like this near the what it was the shore of the ocean on Mars or the Arctic would be an excellent place. The advantage of the Mars Science Laboratory is that it is an instrument, a rover, that is using nuclear energy. So we don't have constraints on where it will be landed. That will be decided by other teams, members, but it's open to equatorial region up to the poles. But we haven't decided where it will search. A good possibility is where we have evidence for liquid water, like jarosite sites or clay sites or the Arctic.
Other questions?
There's a question here.
And how deep, if there is a groundwater under the Atacama Desert, under the surface?
How deep have we dug?
If there is a groundwater under?
Oh, that is a very interesting question because ironically, the Atacama Desert is a hyper-arid desert, but in the Central Valley, where there is no water, no rain, the water depth is 20 meters down. But it's very far for bacteria or water to diffuse. But when we are working in the Atacama, we just have a hole, a drill, and we pump the water without any problem. It's very near the dry zone.
I actually had a question. How long will the Atacama Desert be bacterialess when NASA and ESA people start roaming around?
Well, that was a concern we have several years ago, but we conducted an experiment in which we took students from UNAM and Louisiana State University. We covered an area and we asked them to do everything, have lunch, take their shoes, walk around, and then the day after, we sampled for bacteria, and they were all killed. There were also experiments in which we brought bacteria from the south of the Atacama into the cold region, and they were killed within 1 or 2 days. The reason is that the UV light is so intense that it produces mutations, and in the absence of liquid water, bacteria is unable to repair these UV damages on the DNA, and they become irreversible and they die. If there would be moisture, then they can do the repair. So we have no concerns about walking there and contaminating because the bacteria will die again soon. Also, when we come to the Atacama and we have camps, we bring insects from the fruits into the camp, and we see flies or other insects in the camp, but as soon as we leave, they die.
Okay, let's thank our speaker again.
Thank you.